Hey everyone, this is part 5 of the videos going over test 4 review. We just finished talking about our plane mirrors. Now we're going to look at ray diagrams for mirrors and lenses. Just put it all together because they're all very similar. So I have given you on your equation sheet, which you can see over here on the right side, you can see I have given you these same 6 diagrams that you can see right here in this test review outline. So these are available to you on the test, so you don't have to try to memorize what they look like, but you want to understand how each ray diagram is formed. So the first thing that is the same for all of these diagrams is that you have the optical axis drawn, that line going through the center. Then you have your object drawn as an arrow. And then you have your 3 special rays that are drawn. These orange rays in all of these diagrams are all the same. They're all the rays that start off parallel and then they go through the focal point. You can see with this converging mirror here and with this converging lens, it's parallel, then it goes through the focal point on the other side. If you have over here another converging mirror, it's parallel and through the focal. Parallel and through the focal. The only time it looks different is if you have a convex mirror, then it's parallel and then it appears to come from the focal point, but it actually doesn't go through the focal point. Same thing with your diverging lenses. It's parallel and then it appears to come from the focal point on the same side. And then the second ray is the ray that goes through the center of curvature, reflected right back if it's a mirror, but if it's a lens, it goes through the center of the lens and then it just keeps going through. So that ray is the same for all the diagrams. If your object is over here, then the ray has to appear to come from the center, but then it's still going to be reflected back. So there's always a line that hits the center and the object and then is reflected back or goes through that lens. Then the third ray is the one that, and this one seems like it was misnumbered, some of these here, but ray number 3 is my purple one. Number 3 is the one that goes through the focal point and then is reflected parallel, or if it's a lens, it's through the focal point and then parallel on the other side. So once you understand those 3 rays, then it's easier to see how the image, where the image is formed, where the rays intersect. And then you can tell the different properties of the image. Is it real or virtual, etc. So you can see in this case that the rays intersected there, so that's a real image. Same here, the rays intersected, it's real. But in the other 4 diagrams, you can see that the rays had to be traced back because the rays here never intersected, nor here, nor here. These rays here, after they reflected, they never intersected. So whenever you have those dashed lines that indicate that your rays were traced back, those are all virtual images. And then you have to be able to tell if it's inverted or upright. You can see upside down is inverted, upright is the same orientation as the original object. And then you can tell if it's smaller or larger. You can see here that the image is smaller than the object, but in some other cases like here, the image is going to be bigger than the object. So keep in mind that these 6 diagrams are not all of the diagrams. We did learn a couple of modifications which were for these top 2 here. So we learned that the object produces a smaller image if the object is further than the center of curvature. But what we're missing for here is the ray diagram that we actually did in an example that showed that if the object was somewhere in between C and F, then the image was actually bigger. So looking at these 6 diagrams doesn't tell you for 100% the size of the image, because this image can be smaller or bigger. Likewise with this image here, it can be smaller or bigger. It's going to be smaller if the object is further away than 2 times that focal point. It looks like here it's about the same size. That occurs when it's exactly at 2 times the focal point. If the object is further, it creates a smaller image. But if the object is somewhere in between here, it's going to create a bigger image. So you don't have to remember that, because you should be able to draw those ray diagrams. But just know that you're able to use these 6 given pictures to know the other properties, such as real or virtual, or inverted or upright. Lastly, if you look at these 4, these always tell you the accurate size of the image. The concave mirror always produces a bigger image when your object is closer than the focal point. And the convex mirror always produces a smaller image no matter where the object is. For your lenses, if the object is in between the lens and the focal point, the image will always be bigger. And then a diverging lens will always produce a smaller image. Okay, that was a lot. So you should be able to look at these diagrams and figure out these properties, draw the other 2 diagrams that are missing that we did in examples, and then you should be able to use the thin lens equation here in order to find the missing value. Whether you're asked to solve for P, Q, or F, you should be able to solve for it. We've solved many times for Q, but if I just show you for P, if you have 1 over P, and then you subtract the 1 over Q to the other side, you should be able to solve for P. The same way that we solve for Q, you want that common denominator, so you can multiply this denominator by F and this one by F, and over here you multiply this by Q and this by Q, so that now you have a common denominator, so it's Q minus F over Q times F. And then to solve for P, just flip both fractions, and you'll get that P is equal, this is Q times F here, and you'll get that P is Q times F over Q minus F. I always recommend solving for the variable first and then plugging in the numbers. Otherwise, it's hard to make mistakes with the negatives. Sometimes your focal length might be negative, etc. So that is really a key thing here, is to really pay attention to the sign conventions. I have given you this table to remind you of the important ones. So you can see here that if you have a mirror and the focal length is in front of it, that's a positive. That's a concave mirror, the focal point is in front. If the focal point is in the back of it, that's a convex mirror. Then that focal length is going to be negative, so make sure to use that negative into your equation. And then your converging lenses have a positive focal length. That's your lenses that look like this are the convergent ones, and the diverging lenses always have a negative focal length. The last two equations I forgot here. So if you are given a mirror and you're given its radius of curvature, that corresponds to the distance here from the mirror to the center of curvature, that's R. Make sure to divide that by 2 to find the focal length. And then the last thing is, if you have a combination of lenses, 2 lenses used after another, for example, then when you have that first object then wherever the image is created for that first object, let's say it's created here, then this image now becomes the object for the second lens, and you can use this equation to find the magnification of the final image by just multiplying the two individual magnifications together. So that's about it for lenses and mirrors. You want to be able to manipulate the thin lens equation. Make sure to use the correct signs for the focal lengths. And you also want to be able to know, well, if I get an image here that is a real image, it's in the back of my lens. I can look at my table here, see that Q is in the back of my lens. That's a positive Q. So you don't have to memorize any of it, but just know how to use all of those sign conventions.